Hello, my name is Matthew Prata, and this is assignment 3, um, measure and transmit fan speed and thrust using the Arduino-based optical tachometer by C.M. Palmer. So this is my circuit design. I have the photoresistor connected to A1, or the analog read pin, which then is linked back down to ground through the photoresistor, but is connected via a voltage divider on an external 5-volt source and an external ground. You'll see I had to tie the Arduino ground to that ground so the analog reference doesn't become unstable. And for the for the IR diode, I just have it directly connected to a 5-volt pointing directly at the photoresistor. Now, when something gets in the way of it, you'll notice that it blocks, and my analog pin will be able to differentiate that. So how do we take our analog signal and convert that to revolutions per minute? So we first have our analog input. We find that thresholds, and we look for rising edges, or when, in my case, the fan blade is blocking the photodiode. We then find the differential between rising edges, and we divide that by the number of blades, and we can figure out the RPM. Because there will be ambient IR in the room, we'll have to use the first 5 seconds to calibrate our device and find that minimum threshold for the up clock signal. Also, our up clock signal won't be that clean. There'll be steps in it, and so we'll have to use that threshold to define when we're above and below. Okay, now let's look at some of the code. So at the top you can see we have our RX initialization pin and our LED pin. These are just some constants. We then also specify the number of blades, the calibration time, the run time, and how often we print. In addition, we have our edge minimum microsecond period and our maximum. This is to help denoise the system. We have our serial baud rate, and then we also have our state machine where we have calibration, we have our run, and then we have our done state. That will be seen in our main loop. Here are some of our global variables, such as like what state or the raw analog reading, and the last edge we received in milliseconds, the RPM values, what we write out, and so forth. Here are function programs, and here's our function queue, because we're using function queue scheduling. Each one has their different priority. That's how we specify. So the first one's the timer, and the second one is the last written value. In this case, we have our setup, just basic setup. And then here's our main loop. So we have our calibration stage where we read the analog, do a digital write, and we keep looping this for the threshold of the time. And once we're there, we get our baseline reading values, or our threshold as discussed before. We then move to our run phase after this, and we serial print all our baseline. And then our run phase, we iterate through our tasks, but we also check if the task period has been allotted. And if not, then we'll skip it, and then we'll go to the higher priority tasks. All right, so we have our task sensor reader, which is just a raw analog read. And then we have our edge detection algorithm, which makes sure we're in the lower part. We then check for the rising edge time. We look if we've had a last one, and then we compute the RPMs based on that differential. And this is us resetting the last edge. So then we have our task print in frequency. We check for that edge time, and then we print the output from the RPMs and the readings. And then at the very end, we have our blink task, which is called to let us know the program's running. Here we have our basic serial reader. It's very similar to the last one, but this time we'll be parsing our CSV, and we'll be outputting the RPMs in real time. And then we'll also be saving it as a CSV later. So for this demo, I'll be using a DC motor connected to a separate power supply at 3.3 volts. As you can see, we have the two sensors connected. They both have blocking around them. I also put tapes on the DC motor so it blocks the IR better. All right, so I'm going to run the serial reader. Right, as that runs, it has to first get calibrated. You can see the blinking light in the calibration, and now we are calibrated. So if I put my finger in front of it, you'll see it'll tell me the revolutions per minute it thinks if my finger was 3 blades. Anyways, I could turn this on by completing the circuit. All right, so we'll complete it. I'll put it in front, and then you'll notice we got a spike at 5,000 RPMs, and it'll be adjusted. And if you wanted a really accurate reading, you would take the average across time. Obviously, it doesn't help that I'm moving around. And you see we've gotten a peak, but I would say it is roughly around 5,000 RPMs. Now to also really test, I will be switching the input voltage to 5 volts, which in theory should increase the RPMs of the DC motor. All right, so here's the reading for the 5-volt DC motor. If you recall, the 3.3 volt was giving us around 5,000 RPMs. So let's just prove that our tachometer is reading faster RPMs. Right, as we connect it, we put it in front, and you'll see it immediately spikes up to 6,000. But as I steady my hand placement over it, we get ceilings at around 10,000 RPMs. And of course, you'd want to average this out over time, or also take out the variability of me holding it. In addition, we save it to a CSV, so you can pull it and post-process the data as you please.